Okay, and now let's start then with the next chapter, which is already area and trigonometry in the hyperbolic plane. And then I'm going to start really with trigonometry, with hyperbolic trigonometry. So first, with the angle of parallelism. So maybe let me try to see if I can show you an animation. Because somehow something that we have not stopped and discussed is okay. So how about the fifth postulate of Euclid? Right? Like at some point, kind of that's one of the motivations I gave for why it is interesting to study hyperbolic geometry, but I haven't said really anything, right? So today I'm going to say something. Oops. Yeah, and so you see, like, what I'm going to do, what I for the postulate of Euclid, right? One takes a straight line, so a shortest curve, and a point outside, right? And then one asks, and then the postulate says that in Euclidean geometry there is exactly one shortest curve through the point you chose outside, which is parallel to the given shortest curve, right? So which doesn't intersect it, right? And now there's actually infinitely many, and here you can see, like, here there is one, right? And then of course all you keep seeing now many of them, right? So is it visible? Yeah. Right. So here you can see how the fifth postulate of Euclid stops holding in the Poincaré disk, right? But then somehow you see there is a range. Right? So something. Yeah. You see it's like the shortest curves through the point parallel to the original shortest curve. They really move like in a range, like in an interval range. You see. And then somehow that this range is really given by this angle that you are seeing, this angle that you are seeing here, right? Or if you want, alternatively, by the complement of the angle of this angle here, right? Which is just twice this angle, which is this angle. You see, it's like I just throw a perpendicular to the given shortest curve, right? A hyperbolic perpendicular, right? So this is again a hyperbolic shortest curve, and then this angle is equal to this angle. So it seems that everything is can be measured just like that. This range in which the parallel can kind of run through is can just be measured if we measure this angle, right? Which is like half this angle, and of course this angle is just the complement of the angle where the parallels run through, right? And here in the program you can actually see here when it says this angle, it really the angle that it's measuring is really just this one. Okay, so half this. And then something that you can see is that angle, the value of that angle actually changes if I move the point. Right? So somehow the value of the angle that gives you the range of parallels is not really the same for all points outside the given shortest curve. Okay. Now, this angle, which is half this other angle, is what we call the angle of parallelism. Right? And you can see the name. Why is it called angle of parallelism? Well, because it really gives you the angle of the range where parallels can run. And that's the next thing. That's the first topic in this section. So in that situation, so you see, so here I'm really reproducing the situation that you saw before. What I'm given is a shortest curve and a point outside, and then you see I throw the shortest curve from this point to this point in the unit circle, which, by the way, this one is parallel. It's kind of is a parallel kind of in the extreme of the range, because this point is not in D. So this apparent point of intersection is not a point of intersection, at least not inside the Poincaré disk, not in D. Right? So this one is a parallel, right? And then I throw a perpendicular, yeah, and this angle is what I call the angle of parallelism. So this is the angle I was mentioning, which is half. Well, okay, so let me see. I think it's this. Yeah, so it's half this angle. Okay, and I call it, as I said, the angle of parallelism. And we have this nice theorem, which is that angle of parallelism satisfies this identity where A is this length. So if you want, A is the distance from Z0 to the given geodesic. Okay, yeah. Yeah, so do the following. Take I mean, this is a shortest curved segment, but so it's contained in exactly one full shortest curve, right? Like that really goes, yeah, that whose extremes are in the unit circle. So I prefer to call it the circle at infinity, to emphasize that its points are not part of the hyperbolic plane. Okay, now reflect along that shortest curve. Reflection along that shortest curve preserves angles, just kind of preserves, but at least in absolute value. Right? So if something is orthogonal, its image is also orthogonal. So this means that this shortest curve segment really is mapped to this one, right? So that under that reflection, really this one goes to this one, and the other way around, this one goes to this one. Okay, and if you see, since this ray goes from this one to this point at infinity, which is this extreme of the yellow shortest curve, its image is the point, the other extreme of the yellow shortest curve, right? This is fixed by the reflection, right? And so this angle is equal to this angle. Okay, and now like that such reflection exists. Well, you can first argue saying, take a Mobius transformation preserving the disk bijectively that moves Z0 to the origin. Then this one is or if you want, the full geodesic is mapped to a geodesic through the origin, which is just a straight line segment in that case, and then for such straight line segment, one can easily see that there indeed exists a Riemannian isometry, which is just a reflection along that line. Okay, so indeed it doesn't matter, right? Oh, okay, so that this is equal to this. Yeah, thanks. Yeah. Okay, now let's prove the theorem. And now what I'm going to do is I'm going to prove the theorem in a specific situation in another model in the upper half plane. So what I'm going to do is this point I send it to I, and this shortest curve I send it to the positive part of the imaginary axis. Okay, and then applying a rotation, you see an elliptic transformation if necessary. I assume that the point Z0 lies to the right of the imaginary axis. So all of this I can do up to applying Riemannian isometries that preserve the orientation. Okay. Right. So you see the point is that here since I'm sending this intersection point to I, this length simply becomes the distance from Z0 to I in the upper half plane. Okay. So this means, so let me see. So first, yeah, so let me see. Right, so first of all, you see the cosine, the hyperbolic cosine of this distance, we saw that it was given in terms of a formula, right? And this is the formula, right? Where it was 1 plus some expression that was invariant under applying Morris transformations, right? And so in this case of I and Z0, that expression is simply this one. This imaginary part is just 1, and then imaginary part of Z0, I claim that is the sign of alpha. Okay, so let's see why. You see, alpha is this angle, and what I'm claiming is that this angle alpha is equal to this other angle. Okay, so let's try to see why. When I say that it's that angle, what I really mean is that it's the angle between the tangent there, which just coincides with this one, and the tangent to the circle there, which is some Euclidean straight line, and that's what I really mean. I draw the tangent at this point to the circle. So here I have 90 degrees. Okay, now I keep drawing the vertical here, right? So I have 90 degrees here. Yeah, okay, so 90 degrees there and 90 degrees here. Okay, now when I say that the alpha is really this angle, that's really the definition of being that being. So this is alpha. Okay, now alpha plus 90 plus this pink one is 180 degrees. Okay, on the other hand, alpha plus 90 plus this other one is also 180 degrees. So this one has to be equal to this one. Without assuming, I'm not assuming that this is alpha at all. Yeah. So these two are equal.
Right.
And now I see. Then this must be alpha.
Yeah.
Right. And now I deduce this is alpha. Yeah. Okay. Okay. But so this means that then since this is really the unit circle, this height really is the sine of alpha. So the imaginary part of z naught is sine of alpha. Okay. And now I want to compute this one, right? So z naught minus I square. The square, I'm going to leave it there. But so you see, this is the norm of this vector. Z naught minus I. Huh? Z naught minus I. And I want to measure it in terms of alpha. So what do? You see, I take that straight line segment. I draw a Euclidean perpendicular, and what do I have? Let's say that this is the Euclidean plane, but kind of you have to tilt your head. So this then kind of with respect to these other coordinates, this height is the sine of this angle. Okay. So the length we are looking for is 2 times the sine of this angle. Okay. Now the sine of this angle is, you see, this angle is half this angle. Okay, which is pi over 2, I mean it's 90 degrees minus alpha. So I have to take the sine of pi over 2 minus alpha divided by 2. That's what I do here. Okay, 90 degrees minus alpha, which is this, divided by 2 is only this. Sine of that is this. 2 times the sine of that is this. Okay, so this becomes this. Okay, and now, well, you see, I cancel 1 2 with the 2 here, and then I take common denominator. Okay, and now I use this identity. Okay, this sign remains, and now I have 2 times some square of a sine, 2 times square of a sine, and I can replace it with this other, right? So I replace it. But you see I have to multiply this by 2. So I do it multiplying this by 2. So that's why it's pi half minus alpha. Okay. So an exercise, prove this identity, right? Or at least, search the internet to see a proof. Okay. I am here, and then you see I just use the here it should be here. The kind of the usual kind of symmetry that one sees between the cosine and sine, right? I mean, when one draws the graph of the sine and the graph of the cosine, one really looks like one is the other one shifted, right? Okay, so because of that, you see I just substitute, and there are cancellations, because you see this one then cancels with sine of alpha, and so I get just 1 divided by sine of alpha. But you see, I started with the hyperbolic cosine of A. So this is equal to 1 divided the sine of alpha. So I have what I wanted. Okay. Well, prove those trigonometric identities. Here again, the same typo. And let me now go into the cosine laws, which you see sometimes one may think, oh come on, I mean this what's the point of proving those laws, right? I mean, what do they really tell me, right? I mean, or like if you see the cosine laws in Euclidean geometry, you can say, okay, fine, but what do they really tell me, right? I mean, maybe it's not so easy to see what they really mean. In the hyperbolic plane, it has a very nice, like the cosine laws have a very powerful consequence, which is very visible, and somehow it's somehow easy to justify why they are important. So I'm going to take any hyperbolic triangle with positive internal angles, alpha, beta, gamma, and the length of the sides to be ABC. So you see, it's kind of as usual. If the angle is alpha, then the opposite length is A. If the angle is beta, the opposite length is B. If the angle is gamma, the opposite length is C. That's the correspondence. And these are the formulas for the cosine laws. Now to prove, and you see here I'm writing a kind of a special configuration in the Poincaré disk. Right? In the Poincaré disk, I'm assuming somehow that one of the vertices is 0. Right? And that kind of that one of the vertices is 0, and that one of the sides lies really horizontally, so on the real axis. Right? So okay, and then what I'm going to do is somehow I'm just going to take this and project to the hyperboloid. If I project to the hyperboloid, of course, then one of the vertices is 0, 0, 1. The other one, you see, you remember, right, that it was kind of in a vertical plane, so that's why there's this 0, one of the kind of coordinate vertical planes. And I have to write the hyperbolic sign first, right? Because somehow it's really the kind of the hyperbola really tilted. So that's why on the hyperboloid somehow the cosine appears after the sine always, instead of cosine sine. Okay, and now the third point, you see the third point is somehow one can say, okay, how can I obtain then the third point on the hyperboloid? Well, you can say, okay, for the third point, well, you can take this one with a 0 here, like 0 sine 0 hyperbolic sine of A, hyperbolic cosine of A, and then say, okay, but that one, and then just rotate it horizontally. And when you rotate it horizontally, you have to put, sorry, here of course one of them is wrong. Yeah, you have to put I think it's the, let me think. It's in the cosine. Yeah, sorry. Okay, sorry. Of course, I mean, it's sine cosine. I'm going to put the cosine here and the sine here. Sorry about that. It is. But you see, somehow what I want you to see is that really the way I'm thinking, the way I'm arriving at this formula for the coordinates of the third point is, okay, I take a point that looks like this, and then I rotate it horizontally. So I rotate it horizontally, so the third coordinate doesn't change when I rotate, and then this one has to be multiplied by sine and cosine of the angle I rotate with, right? And then, well, okay, all right, right, and somehow the idea, somehow if you want in the Poincaré disk, somehow what I'm doing is really for the third side, I'm placing it first here and then rotating it with gamma. So that's why it's a cosine of gamma. Right? Cosine of gamma multiplying the length, which would be this a. Okay. I mean the Euclidean length. Okay. Now the point is that the point is that if you remember, we showed that if you give me 2 points in the hyperboloid, the hyperbolic cosine of the distance between them was minus Minkowski's form evaluated in the 2 points. So the hyperbolic distance between this point and this point is minus, sorry, the cos, here, there it goes again. So the hyperbolic cosine of the distance between these 2 points is minus their Minkowski product. Okay, right? I mean, it's here. So the hyperbolic cosine of the distance in the hyperboloid between these 2 points is equal to minus Minkowski product. So it's this times this, minus this times this, minus this times this. Okay, this times this is hyperbolic cosine of B, hyperbolic cosine of A, minus cosine of gamma, hyperbolic sine, hyperbolic sine. Okay, and now what's the distance between these 2 points? Well, you see, the point is that it's precisely C. Because somehow, you see, it's the opposite to gamma. And here, gamma is precisely the one I used in order to rotate. So it really has to be C. So cosine, hyperbolic cosine of C, this is C, is equal to this times this minus this times this. If you look at the formula, it's hyperbolic cosine of C is this times this minus this times this. So it really is a consequence of the formula for the hyperbolic distance in the Minkowski hyperboloid. Okay. Now for the second cosine law, I couldn't find a more direct or conceptual proof. So it's it's like a lot of just somehow brute force computations. Using already the first cosine law and using our hyperbolic identity. I mean the identity between the basic identity between hyperbolic sine and cosine. And computation. I don't want to just read the computation, so I think you can just check it in the notes. but what I do want to stress is, you see, the first cosine law really has a very conceptual proof. Okay, and here comes the corollary, which is really the power of the second cosine law. If you have now two hyperbolic triangles with the same internal angles, but let's say the same internal angles, let's say for the moment positive internal angles, right? Because that's the hypothesis under which we proved these ones. So imagine the situation. So all I know about the two triangles is that they have the same internal angles. That's all I know. And the conclusion that I can draw is that actually their lengths of their sides coincide. So it's not the case that I can think of one of them as being as a rescaling of the other. They really must have the same length. And not only that, one can be mapped onto the other by Riemannian isometry. So you see this Euclidean phenomenon of having triangles of really very different sizes but similar to each other doesn't happen in the hyperbolic plane. And the reason is the second cosine law. If you see the three angles here on the right hand side, only angles appear, and on the left hand side is a function which is injective on positive real numbers on a positive real number. So in other words, I can just apply hyperbolic arc cosine and put C completely in terms of the three angles. Okay, I can do that for both triangles, right? And then I get, okay, so their lengths really coincide. That's one thing. And once I know that, how do I put one into the other? Well, I just start playing games, right? Like I say, okay, in each of them, let's say, once you know how the lengths of the three sides match each other, coincide, then you know how the vertices correspond to each other. Okay, pick one of them in each, like corresponding vertices, and send those vertices to the origin, and then so that things look like this, and then it may be that once after you did that, one is kind of a reflection of the other, maybe. If so, then just apply a reflection. But then you see, you can just start playing a game, almost a combinatorial game, that allows you to put one on top of the other using Riemannian isometries in each step. I like to think of this as, if I have two similar hyperbolic triangles, then they are congruent in the weak sense, because the lengths of their sides coincide. But not only that, they are actually congruent in the strong sense, because actually one can map one onto the other through an actual isometry. Okay, and well, some exercise, some more identities involving hyperbolic distances. And I think that was it for